This project is leveraging ultrasonic cavitation to enhance antibiotic potency and solubility. Currently, there is a limitation to antibiotic reconstitution methods, which have not evolved to meet increasing global demand. Antibiotics such as azithromycin often experience uneven absorption in the gastrointestinal tract, resulting in low bioavailability of only around 37%, and delayed or insufficient concentrations at the infection site. This research investigates whether electrolysis and ultrasonication synergetically can improve antibiotic dissolution and, in turn, enhance bactericidal effectiveness. A major limitation of many antibiotics is poor solubility, especially after lyophilization. While dry freezing these antibiotics improves its shelf stability, it reduces how well the drug dissolves in water once it's reconstituted, which limits how much active antibiotic is available to interact with the bacteria. Azithromycin monohydrate is an example of this, widely prescribed yet inherently poorly water soluble, which can restrict its antimicrobial action. To evaluate whether improving dissolution could overcome this limitation, I tested 4 clinically relevant bacteria, Serratia marcescens, E. coli, which are both gram-negative and diffusion limited, and Staphylococcus epidermidis and Bacillus subtilis, which are gram-positive species, with known azithromycin resistance. Building off of last year's prior successes in increasing zones of inhibition, this year's project focuses on how cavitation can optimize antibiotic reconstitution. Ultrasonic cavitation causes microscopic vapor bubbles in water to rapidly form and collapse, generating extremely high localized pressures and shock waves. These forces disrupt hydrogen-bonded networks in water molecules, reducing average water cluster size. When azithromycin is reconstituted in this water that is treated, the smaller, more dynamic water clusters can more easily orient around the drug's hydrophobic and hydrophilic regions, forming more effective hydration shells. As a result, the antibiotic dissolves more uniformly, increasing the amount of active drug available for antimicrobial action. Electrolysis and ultrasonification were used to modify water structure during antibiotic reconstitution. Electrolysis increases hydroxide concentration, raising pH while disrupting hydrogen bond networks, while ultrasonication reduces average cluster size. Together, these effects create smaller, more dynamic water clusters that improve hydration shell formation and enhance the solubility of azithromycin. My hypothesis for this experiment was that if azithromycin powder is reconstituted with an electrolyzed and ultrasonicated solution of distilled water, then the antibiotic will have a greater zone of inhibition than that of untreated distilled water due to a reduction in cluster sizes, which increases solubility of polar compounds. On the left of this slide, you can see the pH stability modeled by time, and on the right, you can see the variables for mix. On the left of this slide, you can see preparation before the experimentation, and on the right, you can see the experimentation procedure. Please pause to read, or feel free to view it on my research plan. On the top of the slide, you can see trials 3 and 4 for my 4 bacteria. On the bottom left, you can see my positive control group, and on the bottom right, my negative control group. After conducting 7 trials for the 4 bacteria, Bacillus subtilis, a poorly responsive bacteria to azithromycin, showed a pair sample t-test that was statistically insignificant with a t of 0.22 and a p-value of 0.83. Whereas the bacteria on the right, E. coli, after comparing treated to untreated values, had a very statistically significant increase with a t of 3.3 and a p-value of 0.016. In addition, Staphylococcus epidermidis, the graph on the left, increased in mean values from an untreated mean of 2.09 to a treated mean of 2.59. Differences in mean inhibition zones are considered statistically significant with a t-value of 2.46 and a p-value of 0.048. Whereas for bacteria on the right, Serratia marcescens, which is normally highly resistant to azithromycin, had statistically insignificant zone means from mean of 2.06 to a treated mean of 2.33 with a t of 2.29 and p of 0.35. The graph on this slide subtracts mean treated values from mean untreated values, where the data shows that the hypothesis was supported by Escherichia coli by a paired t-test where the t is 3.30 and the p is 0.016, and also by Staphylococcus epidermidis where the t-value is 2.46 and the p is 0.048, but not by Serratia marcescens with a p of 0.35 or by Bacillus subtilis with a p of 0.83. The chart on this slide compares the difference in mean variation, which is treated values minus untreated values, between the previous year's project and the continuation project this year. According to the data on this slide, the previous year's project was more effective at enhancing zones of inhibition for Serratia marcescens, Staphylococcus epidermidis, and Bacillus subtilis. However, this continuation year's project was more effective at improving zones of inhibition for E. coli, with a mean of 3.014 this year, increasing by just over 0.1 centimeters. The increase in E. coli zones of inhibition is likely due to the fact that it's a gram-negative species with highly selective uptake barriers, which is improved by the ultrasonic's ability to disrupt cavitation, which causes a decrease in aggregate particle size. As a recommendation, the synergetic treatment's ability to aid in cell membrane transport may allow it to increase azithromycin's ability to be an anti-inflammatory, perhaps rendering it as an available treatment to viral infections with the new mechanistic treatment, and to test the effects of an increased number of gram-negative bacteria, as cavitative pressure seems to add to zones of inhibition for these species. And a future application of this project would be improving the solubility of other compounds that are difficult to dissolve in water, such as highly crystalline or hydrophobic substances. By understanding the mechanisms behind electrolytic and ultrasonic water treatment, more effective dissolution and reconstitution methods can be developed across a range of applications. Thank you very much for watching and have a good day.